Welcome, everybody. Good morning. While Shushan talked about attacking AV software, I will attack them from a different perspective, and I will talk about attacking AV best practices. The work I present here is joint work with the awesome people at UC Irvine, Stefan Brunthaler, Per Larsen, Stephen Crane, Michael Franz, and Richard Wartel from Manient. If you look at the picture on this first slide, how similar are those bugs that you see? How many different bug families do you see? Actually, all those bugs are the same underlying bug. They're just small genetic variations in the code, in the DNA of the bugs that leads to a very different look of these bugs. And that's exactly what's happening with malware. There are few families out there, and attackers use manual diversification to evade different forms of detection. And common solution for malware detection still rely on signatures and similarity metrics. And in this talk, we'll see that those metrics and practices are no longer effective. So the malware landscape is changing. How many different malware families do you guys know out there? 5, 10? How many of those are actually active at a specific point in time? There are only very few malware families active at any single point in time, and it's like a big monoculture out there. And on the other hand, there are thousands of variants that hit the malware feeds of antivirus companies every single day. So all AV companies are actually overrun by lots and lots of samples. And attackers use different forms of packers to hide the actual code and manually diversify the samples just a little bit so they can get by the antivirus engine. And on the other hand, it's all about the money, right? Attackers generate new samples, defenders classify those samples, and it's just an endless loop that keeps going and going. And usually, as the system is right now, attackers are already at an edge. They can use a very low amount of resources to generate a lot of work for the AV companies. And I'll argue that these resources that the AV companies spend should better be spent for something else. So, for example, research that would actually solve the problem, or better security practices, like we've seen in the talk before. So the malware distribution is like an ongoing arms race between attackers and defenders. And it always starts with a new malware instance that is generated by an attacker. And it continues, the attacker will distribute and send it out, and attack a bunch of targets, continue, move along, and just spread the malware as fast as it goes. At one point in time, an AV vendor will get a first sample using one of those feeds and distribute it to all the other AV vendors. It might take up to months or years until they have time to actually analyze that sample. And they will do first some automatic and then some manual analysis of that sample and classify it at one point in time. Then they will update their signatures, send it out, and as soon as the sample is detected by a bunch of AV engines, the attacker will re-diversify and send out a new sample. And the game continues. It's like endless fun, right? So, unfortunately, defenders are always inherently limited. First of all, newly diversified samples are just not detected by the techniques that are used on current systems. And every time an attacker re-diversifies, it is basically a new attack. And we have to start the whole spiel again and just redo it from scratch. Also, the attacker has a specific edge. New malware spreads very, very fast. Updating signatures and distributing might have worked in the early 90s, but nowadays when you can infect all the computers that are on the internet in the matter of minutes or hours, it just doesn't work anymore. You need to find other ways to protect. And the defenders usually have to fight the time lag between the analysis and the updated signatures, which takes a huge amount of time in between. Now the question is, can we automate this process? AV vendors know this or have known this for quite a while now, but they are still locked into these old practices, and they just don't want to move along. Now the question is, from the attacker's side, can we give an additional edge or even a higher edge to the attacker? And yes, we can. So the core idea is that the compiler is at the core of an efficient automation. And we can use different compiler techniques to enable a faster and more thorough diversification of individual binaries and then attack the systems even faster. In this talk, I'm introducing fully automatic diversity for malware. And it's basically an additional attack that thwarts any similarity-based matching. And it should drive the point home that similarity-based matching is not the solution. It's time to move along and get on better security practices. I'm inherently lazy, so I don't want to run a lot of code and a lot of manual work to produce my huge set of malware binaries. So I'll just use some automation, right? And a compiler is the perfect place for that. So if we have the source code of a specific application, we can run it through the compiler, and it usually generates one single instance of malware. And the current practice is that attackers use the generated binary and then run packers on top of it to generate individual samples. These packers are very limited because they just work on the actual machine code. And the compiler or a regular compiler will always produce the same binary. But we are adding a different edge. We are adding a randomization component in the compiler and using some flexibility in the language to produce a different set of malware every time we run the compiler. And I will go into more detail later on in the talk, but that's basically the overview of the technique that we will use. So it's compiler-based diversification, where lots of information is available, and we can run a lot of fun stuff on top of it. So the outline of the talk is as follows. First, we will discuss the state of the art of malware detection, what is actually out there, what is used by the current machines. Then we will introduce malware diversification as a new threat, and in the end, quickly talk about some possible mitigation strategies or better security practices that could work on top of that. So what is the state of the art of malware detection? How do we find malware, and how do we find these vulnerabilities? So we have to know that malware detection is inherently limited in 3 ways. First of all, performance. An AV engine should not slow down your computer too much. So there's only a very limited amount of resources that you can spend on detecting or to see if something is actually malware or not on an individual computer. Second, malware scanning is always limited due to the precision that it can get. Based on the similarity metric or the detection techniques, you will always run into false positives or false negatives and a whole bunch of errors, and it's just a pain. Also, latency is the third limitation. There's always a very long time lag, as we've seen in the circle before, between the initial spread of a malware sample and the time that actual users' machines are protected from that malware. So we'll look into the 3 different ways of detection mechanisms. First of all, the oldest detection mechanism is signature-based. So we're using a simple signature to compare it. And if you're wondering, by the way, that's George W.'s signature up there. The second one is static analysis. So you're running some analysis on top of the binary, but you're not executing it yet. And the third one is some behavioral-based matching, where you're running the binary either in a sandbox or some other analysis scheme on top of it to extract additional information out of it. And each of these approaches has its pros and its cons. And we'll look into more detail a little bit of each of one. First of all, signature-based detection, which is the bread and butter technique for AV. And it has a lot of advantages, to be honest. It is very fast and very well known and all that. And the idea is that you compare the binary against a database of known bad samples. So you have to match a pattern. There are different kinds of similarity metrics that they have, different substrings or regular expressions or anything else. But the idea basically is that you have a big database of known bad examples, and you're matching the current sample that you're analyzing against a set of known bad ones. And advantages are that it's very, very fast, and it has a very low false positive rate. If you're a little bit clever about how you encode your signatures, you will have a pretty good match. Unfortunately, the precision is limited to known bad samples, and it takes time to update the signatures and to spread it, and there's that big latency involved. The second analysis technique is static binary analysis or static analysis-based detection, and you search for potentially bad patterns and like API calls, system calls, and it's like a lot of heuristics that are run on top of it. And you're trying to detect those heuristics on top of it. The advantage is it's low overhead. You can just run the binary analysis and extract that API calls and then decide if it's good or bad according to a specific score. Unfortunately, you'll introduce false positives along with that technique. And depending on how precise your heuristic is, it can actually be quite bad. And also, it's based on well-known heuristics. If you're a malware writer, you can try to evade those heuristics and get around it. And finally, behavior-based detection, which executes the file in some form of emulator, virtual machine, or something like that, and detects possible bad modifications on top of it. It's the most precise if the malware does not try to evade detection, or it tries to evade the emulation, or there's some other kind of bug involved. But unfortunately, it comes with very high overhead, and usually you cannot spend that much of time on a user's machine to detect that for every single sample. So, to summarize, malware protection, to summarize the current practices of malware detection, there's a large attack surface. It's very hard to detect, and there's basically an arms race between manual diversification and the actual AV engines. And the signature-based detection techniques or similarity-based detection techniques already lose precision or effectiveness against the manual diversification. Also, the defenders have to cope with a very limited amount of resources. First of all, on the target machine for the analysis in the lab, and to push out new signatures as well. And there's no perfect solution out there. Either you'll have false positives and or negatives, or a huge performance impact, or all of them together. So we're already hosts, but can we do actually worse than that? And we'll look into malware diversification right now. So let's move from packers on the binary level to the source code level and to the compiler. And we'll use automation to generate millions of malware binaries that are no longer similar to each other in an instance, and just pop them out as fast as possible. And we'll use software diversification for that. The techniques works as follows. Usually, a compiler translates from a high-level language to a low-level language, and the compiler translates between these two formats. The language specification defines the amount of transformations that are allowed, and many or most programming languages actually have a large set of undefined behavior. And the compilers use that set of undefined behavior to actually optimize the application. And any good compiler makes a deterministic best guess according to what you do. But we'll throw these best practices out of, we'll remove those best practices and add randomization in the compiler. And according to that random value, we'll just modify the compilation process and generate different binaries all the time. And if we, for example, look into C and C++, those languages offer us a lot of liberties that allow changes to the runtime layout and to the compiled code. So, for example, we can change the data layout that's out there. Data structure layout on a stack, we can reorder local variables on the stack, we can run a simple escape analysis and reorder structures across the whole program, and so on. And there's a lot of stuff we can do just for the data layout itself. Also, we can change the layout for the heap objects, we can modify all that, and it's pretty fancy what we can actually do. And for code, we can even do more than that. right? So for example, we can play around with the register allocator. So we can just shuffle the kind of registers that are used. We can starve the register allocator to produce more spill code and all that. And we can do all the fancy stuff so that any produced code will not look similar to any other sample. We can change instruction selections, or we can even work on a more higher level on the basic block level by doing basic block splitting, basic block merging, and just shuffling those basic blocks around so that we can maximize the differences between the different binaries. So if we take these concepts from software diversification to malware diversification, we see that right now we can start off with any software diversifying compiler. And like I just explained software diversification, right? The original goal of software diversification was to protect running applications against any exploit, so that an exploit will only work on your local machine. But we can use it for bad practices as well. And we'll look into diversifying compilers geared for malware. So the idea is we generate unique binaries and minimize common substrings, either code or data, across the whole binary, so that it is no longer possible to use any kind of similarity metric to compare those binaries. Performance overhead of the binary that runs on your machine is usually not an issue for us, and we don't care if the compiled malware has 20% overhead between different samples. Also, we diversify both code and data layout and look for maximizing differences between individual samples. Also, we look into static data as well. You don't want the simple string command giving away all your secret values that you use or secret strings that you use. We've implemented this on top of LLVM. It's fully implemented, small changes to the code generator, code layouter, register allocator, stack frame layouter, and so on. And also some data obfuscation passes on top of it. The input is actually LLVM bitcode. So we are pretty general. If it compiles to LLVM bitcode, we can just generate a diversified binary out of it and spit out as many binaries as possible. But as you know, this is a research product or research project, and the code is very messy. So as an academic, I unfortunately cannot release the source code. Just kidding. I'm not like any other academics, and we'll just release the source code on GitHub, and you can just fork it off and try it out for yourself. So we've implemented all the basic diversification techniques we run on top of a software diversifying compiler, and we have a set of static diversification techniques on top of it as well. So you can just use it to diversify all your static data. As I said, well, I have a couple of help files to get you started, but some of the codes and edges are pretty rough, and we'll add more diversification techniques as we go along. And especially for some kind of graph-based matching, where you try to extract high-level graphs on top of the generated code, you could still use some similarity metrics that would thwart the current diversification. We're working on those, but there's a first part of the code, and you can get access to it. So let's have a look at similarity metrics. This is a simple graph of a bunch of programs. We used mostly the spec CPU applications and generated a bunch of different binaries and compared those two binaries with each other and looked at what kind of the longest common substrings in bytes was between those different binaries. And for most of the binaries, we see that like there's basically no subsequence that's longer than 20 or so bytes. And these 20 bytes is usually just a function prologue or a function epilogue, like passing a couple of arguments. And those are usually not good signatures for your AV engine. So it's already pretty effective if you're just comparing the files in a very simple way. I hope it didn't crash. Let's see. Oh, it did crash. Huh. There you go. So the next slide was a demo anyway. So we'll just move that over and see if we can start the just the demo and save it that way. We've seen yesterday that demos usually work pretty well during presentations, right? So let's just try our best. Here I am running on a very simple, low-scale netbook. So the CPU is not too good. Let's just look at the simple file that we look at. And it's a very simple C file. Just to show you the power of the static data diversification, we have a bunch of strings. We do have a string copy and 2 printfs, and we're good to go, right? So if we run it through GCC, we get the binary, and it prints the stuff, and we're good to go. We look into strings. Oh. And we see we have hello world, foobar, arguments, This will give it away. So let's just try to diversify it for now. We run it through the diversifying compiler, and we have produced a nice little file. And if we go down, we see that all the static data has been encrypted using our magic XOR encryption right now with some random values. On the plus side, we can just use any one-time pad. And whenever we start off, the compiler adds decryption code that just decrypts the data on the fly and generates the code automatically and runs that code through the diversifying compiler as well to change the code layout of that. You might now wonder what the speed implication is. How fast is that stuff? So let's just run or generate 100 samples for this simple program. And you see it goes up. You see the random number somewhere out there flying by. Yeah, it's 65, 70, 80, 90. And we've generated 100 different binaries just for this simple 5-line C program. It's fairly fast. Do you guys want to give me 2 random values between 1 and 100? First number? 32? 42? 2 non-equal random values? $42 and 44. And we see there's a lot of differences between the 2 binaries, and that's just for the very small, simple example. Even like stack frame invocation, different stack frames, and we use the same optimization settings and all that. And we see that there's just a huge differences, just for that very, very small 3-line program that's out there. And if we move down to the code, to the actual data, we see that the data is very different too. So you might wonder, does it actually work? Let's just compile it. And it's the same, yeah. So it actually runs. Now let me try to recover the presentation that died. Why does S-Office crash all the time? Somebody should fuss that software too. No, I don't want to recover. And that's the demo effect, right? That does it to you. And we're back, yay. Maybe I shouldn't have plugged in this random presenter that I found here on the speaker's desk. So we've seen the demo. It worked fairly well, right? Go play around with it. It's open source. We'll add more stuff as we go along. And this was basically the first scenario that I just showed, right? So we do have a compiler out there, and we just use it to spit out as many different binaries that we have. And you've seen that it's pretty fast, right? You can let it run for half an hour, and you will have a couple of million examples. The big advantage is that we just run on the LLVM bitcode. Therefore, we can. It is a very quick way to produce different diversified samples. A second scenario that we look at is a self-diversifying malware. And right now, this is not fully implemented, but we've played around with it for a bit. So usually, you have your static malware binary that you send out to infect or to run on other machines. We'll just add an LLVM optimization core on top of it that is added alongside with the malware. And along with that, we add the malware bitcode and the LLVM bitcode. So we can use, in the malware itself, we can call the LLVM optimizer that just diversifies the bitcode and of the malware and the LLVM core again, and produces newly diversified malware as we go along and spread from system to system. And basically, every time it tries it uses a new random value and just goes along. And we'll have our self-diversifying malware that has even stronger guarantees than any packer, or stronger, bigger changes than any packer can give you. What kind of mitigation practices or kind of mitigation strategies can we follow? Well, we've seen that any signature-based protection is basically host. Do I win with these 10? 10 out of 10? I'm awesome? Nice. So let's look at what we can do. First of all, we see one option would be to recover some high-level semantics from the code, extract some deeper behavior on top of it, which is fairly hard and will result in yet another arm race between malware writers and the defenders. We can do full behavioral analysis, which should or will catch malware at any point in time, but this is very compute intensive, and we have to think about if we actually want to use all these resources for that. Or prohibit the initial intrusion and fix the broken software, educate user, and just educate them enough so that they don't run any random software that hits on their system. Let's conclude. This is an attack talk after all, right? I'm not here to give you the solutions for it. First of all, diversity evades malware detection. And we have built a fully automatic diversifying compiler that you can run on any malware and just spit out as many samples as you want. There's no need for packers anymore, and you can get much higher quality by just using the diversifying compiler. Also, we can adopt to new Similarity Matrix as we go along. And we're moving from an arms race between attackers and defenders to an arms race between defenders and compiler writers, which gives the attackers much more power because it scales much better to just change the compiler once and then open source it and other people can use it on top of it. Lessons you can learn on top of that: don't rely on any simple static similarity matrix that can just be mitigated with very simple tactics. Move along and get better security practices in shape. And with that, I would like to end my talk and ask for any questions that you guys might have.
How many bits of entropy do you think, the diversification entropy, do you have with your engine? What would you estimate? So you do reordering and so on?
That's a good question. I have no idea.
Yeah.
I would say a very huge amount. Like the longer the program is, just take a simple if. At any if, you can swap the if condition for your program, or just look at compiling. When you compile a simple function, you can just change the register order at any single instruction, or just instrument add a new shuffling part. And if if you don't get enough bits out of that, you can always add garbage instructions, right? So at the compiler level, you can just take another application and weave that other application into the translated code, because you know which registers are currently taken, right? So you can just scale it up as far as you want.
Can I ask another question? Halvar Flake, Thomas Dolian did in 2010 a VX class and MD hash algorithm, which was a fuzzy hash where it was resistant to certain types of these type of diversification metrics. Did you measure something against these more fuzzy?
Yeah. BinDiff is actually pretty good at detecting our diversification right now. On the downside, it runs for a couple of minutes for each binary. So it's just more compute resources that you spend. In addition to that, we are looking into ways how we can defeat that too, by changing the control flow graph and other things. So we are running in a compiler, right? We can add more and more stuff to it.
Last question. I saw Michael France's work in 2008 on diversification against buffer overflows. When he just started it, I saw he got a lot of DARPA grants. I thought this was used in the App Store with Apple to create unique binaries for every download. Is that true?
Not in the App Store, but I guess it was used in Mozilla.
Mozilla, okay.
So that was his initial use case, to produce a new binary for everybody that downloads it. Just push the compilation into the cloud, and then everybody that downloads the binary gets its own individual binary, and if you find an exploit on your local version, it will not run on any diversified version somewhere else. We've added the data diversification on top of it, and we've changed some other stuff for this work here.
Hava.
All right, two questions. The first one being, what is the advantage of this infrastructure over Zombie's ZMist engine from 2002, which just takes a binary and then lifts it and starts inserting itself? And the second question is, there's a tool built by the University of Ghent that in 2005 did all the instruction diversification and control flow flattening at the same time. How is your tool better?
Let's answer the first question first. You're always limited if you lift from binary only. For example, all the data diversification is much harder if you just lift. You can do all the code diversification, or a lot of the code diversification, by doing binary code lifting, but you will have a very hard time changing the data structures. For the second question, can you say again?
So there's a tool called Diablo by a bunch of researchers at the University of Ghent, and I think it's by now pretty old. It's from 2005 or 6. And it's modification to GCC that does both modification of the instruction stream, but also fully implements control flow flattening and all these other things that will screw any form of structural matching. How is your tool better?
I'm not too familiar with the other ones. I will have to look into it. I guess do they do the data diversification as well?
I'm not sure whether they do data diversification, but I mean, that's what, a 10-line change?
Well, you have to run escape analysis, right? And look for if your data structure is at one point in time passed into a kernel data structure, or into a system call, or anything like that. So it's more than 10 lines, but yeah.
How effective your approach would be if you use this against a product like FireEye? You know, at the end of the day, it does the same thing. Hello world, hello. So.
FireEye runs runs your sample in a virtual machine and tries to extract some behavior. For that kind of protection, I would just wait a couple of minutes or do random, either virtualization detection. You can add that on top of it in the compiler as well if you want to, or run just a long delay before you run your malicious activity.
No,
FireEye is mostly behavioral-based detection,
yeah,
right?
My question is if the tool is looking for behavior only, not looking for differences in the binary.
Yeah, but it runs with a lot higher, much higher overhead, right? So you're spending more resources on that.
So eventually you're going to bundle the LLVM optimizer, which has also been diversified. And have you looked at what the size of the binary will be at that time?
Yeah, it's a couple of megabytes.
Right.
Did you have a chance to run your stuff against VX class?
Not really.
Okay. What about, have you tried against any clusterization engine that is able to pick up polymorphic malwares and group them to see if they are part of a tree, part of a branch, or they are on their own?
We tried to extract such behavior by doing some more informed matching, but it was not very effective.
Okay. All right. Cool.
Okay, so a few months ago, some French guys released an open source project named OLVM, which seemed to have a lot of overlap with your project. So can you comment about that?
They copy it.
OLVM.
What project?
OLVM. LLVM obfuscation.
Okay.
OLLVM.
It's also open source.
Do you know about this
and
project?
they released it like a few months ago.
Yeah, he doesn't know about this project.
So I think there's a lot of overlap between your project and that project.
Okay, it seems to be a pretty hot topic, right?
Yes.
So there are different diversifying compilers. There's the one by Michael Franz. There's one from Purdue that works on top of GCC and all that. But most diversifying compilers focus on software diversification for security purposes. And this kind of spins the view towards a more attack-based approach.